So, all right, yeah, turn the corner in the course material. And talking about transition metal chemistry, build on all of the d-orbital splitting work we've done, but it's going to be a lot more about chemical reactivity and counting of electrons, things like that. I really love this material. Bread and butter of a lot of inorganic chemistry, just molecular chemistry. Okay.
Just check to make sure that it's got my mic. That's good. All right. So organo transition metal chemistry is about complexes with metal carbon bonds, and metal carbon bonds are pretty strong. Surprisingly, people used to think they were not, and then ferrocene was discovered, which is a total rock. Very unreactive, stable molecule, forms in the pumps at oil refineries. Oil refineries that were separating out dicyclopentadiene were slowly converting their pumps into ferrocene, and they used to have to open them up and shovel the stuff out. And so metal carbon bonds are strong, and they give rise to very large ligand fields. Let's see here. So you're used to the 8-electron rule, but in transition metal chemistry, there's the 18-electron rule, okay? And actually, sometimes it's the 12-electron rule. But usually people talk about the 18-electron rule. That comes from a valence set of orbitals, D, S, and P, okay? You know, so for the 3Ds, you also have the 4s and the 4ps that contribute, which is why we put them in our diagrams. Going above that number of electrons, however, is a no-no. So that's kind of the limit. Lots of the 3D transition metals only use their 3D orbitals and maybe some s. So you find a lot of 12-electron compounds and compounds with less than 12 electrons in the 3D series. Not as common to go up to 18, although there are plenty of examples. All right, so in order to think about complexes and their reactivity, you have to be able to count the number of valence electrons. So we're going to do a lot of examples of that. And you know, things can get kind of tricky. So you're familiar with this example. You take 3 fluorines, you add it to a boron. You get 3 normal covalent bonds, and then you can add other ligands to this guy, because this boron has only 6 valence electrons. It has an empty orbital, a good Lewis acid. You can make these Lewis acid, Lewis base adducts. Now, people think about these as normal covalent bonds. We're going to call them these normal covalent bonds here. Excuse me. We're going to call these atoms here X-type ligands to this boron. Okay, an X-type ligand is a ligand that makes a normal covalent bond with a metal. Not a transition metal here, it's a boron, but principle is the same. Normal covalent bonds are made by what we're going to call X-type ligands. And those X-type ligands really contribute one electron to making that bond, okay? This type of a bond is a dative bond, right? Here, the ammonia is contributing both of the electrons to the bond. And so this thing here is what's called an L-type ligand. L-type ligands will contribute 2 electrons to the metal, in this case, boron. So this nomenclature of X and L is really useful for counting electrons. There are a couple of different ways people count electrons, but this is the way that I like. Okay, so X and L contribute 1 and 2. There's another class also, Z-type ligands. These guys, I'm going to just say they make dative bonds, but they contribute 0 electrons. Okay, they are acceptors. So I was tempted up there to say that the boron is a Z-type ligand to the nitrogen. Okay, that's not what we usually write, because when we're talking about ligands, we're usually talking about things bonded to a metal. And I don't like to say that about nitrogen, but it's rigorously true that the boron is like a Z-type ligand to the nitrogen because it accepts 2 electrons. It doesn't contribute any. Okay, so you already know the definition of valence, right? Valence is the number of electrons used in forming bonds, and you can use this nomenclature X, L, and Z to do valence electron counts. All right, so let's talk about oxidation state for a minute. What is oxidation state? I've forgotten how much we contrasted it with valence yet, but does anybody want to tell me how oxidation state is determined? Is this obvious? Oxidation state is a charge on a metal, and it's assigned by analyzing the relative electronegativities of the substituents around that metal, right? Well, it's not just metal. So you could say, what's the oxidation state of carbon also, right? So if something is more electronegative than the carbon to which it's bonded, it's considered to own the electrons in the bond, and it oxidizes the carbon, raising its oxidation state, okay? People use this term a lot. Relative So I'm writing this out because it's actually a problematic term or idea, or chemists use it loosely. Okay, but there is a rigorous definition of oxidation state as I described it. So let's take a look at boron trifluoride again. Right, boron trifluoride, the fluorine is clearly more electronegative than the boron. And so you can say that this is a fluoride minus and this is a boron plus. And because there are three of them, this then becomes boron 3 plus. So the oxidation state of boron here is 3 plus. Okay. What's the valence of boron? How's valence calculated? You can say it's the number of electrons used in bonding, or the total number of electrons minus those that are in lone pairs. That's the other way we determine it. But the simpler one is just how many electrons are used in bonding. So boron is trivalent. Okay. Now how about ammonia borane? What's the oxidation state of boron and ammonia borane? Still 3 plus? Go ahead, Ethan.
Be 1 plus,
I like your thinking. Why would you say that?
because it was in a 3 plus oxidation state when it was just with the 3 fluorines, but then it accepted 2 electrons from the ammonia.
And so using this definition, can you restate your position?
It's more electronegative than the ammonia.
Electronegativity is a property that we're going to use to talk about atoms. So it's true that BF3 is an acid. Who's more electronegative, boron or nitrogen? Nitrogen's more electronegative. So who owns the electrons then in the oxidation state picture? Nitrogen does, not boron. So what's the oxidation state of boron in this compound? It's 3. Okay. Oxidation state of boron here is 3. What's the valence of boron? Still 3. You could say it's trivalent. Okay, so electronegativity is about oxidation state is about relative electronegativities. Let's do another one. Very handy solvent, methylene chloride. What's the oxidation state of carbon? -2. How many like -2? Anybody have another suggestion? +2? How many like +2? Okay. Anybody else? Or are we settled on +2?
0,
Why would you say 0?
just because it's taking 2 electrons from its hydrogens and 2 electrons are being pulled from the chlorines.
Who's more electronegative, hydrogen or carbon? Carbon is.
Wouldn't carbon be like tetravalent?
Carbon is tetravalent here because it uses all 4 of its electrons to make bonds. Tetravalent, but the oxidation state is 0. Which I think kind of stinks, you know, like that. What do you do with that? 0? When I interviewed for a job here, Jed Parkin asked me this question. And I said 2+. Because I said, well, hydrogen and carbon, they're about the same. But they're not about the same. Well, they are about the same, but carbon is more electronegative, and that's the definition. Jed likes clear-cut definitions. Don't play around, you know, say what you mean and stick to it. So this is 0. And it's confusing. All right, so valence is 4. So I'll just make sure this is clear. Okay. All right. So valence is a much more it's a less problematic term for this reason. And actually, I think most people, when they talk about oxidation state, they're really talking about valence. That's kind of the formalism they have in their mind's eye. But that's not the definition. You're going to hear people use valence in a lot of different ways. I would like you to use the definition that we have provided here. It's a more rigorous one. So, you know, some ligands make multiple connections, like allyl ligands. This is an allyl. And it makes a normal covalent bond here. And so you would call this an X-type ligand because of that. But if you take this compound and you shine light on it, a carbon monoxide will pop off. It's a pretty common trick. Carbon monoxide pops off of transition metals when you shine light on them. And you end up with something that looks like that. What is that I just drew there? A pi allyl. That's what it's called. Yeah. What's going on there?
It's 3 electrons, right?
It donates 3. So you could also write this thing out as write it out like that. What does this mean? Well, it means that the double bond is donating 2 electrons to the metal here. And that is a dative interaction. Okay. So you would call this double bond an L-type ligand, and you would call this metal carbon bond an X-type ligand. Okay. And so people say this is an allyls are LX, right? But they're only that here, it's not an LX type ligand. Here, it's just an X ligand. there it's an LX ligand. Okay, so it depends upon how it binds. People will write the formula for this thing like this. Eta 1 C3H5. Okay. And this guy, they'll say okay, this eta symbol here denotes how many connections it's making to the metal. So how does it do that? Well, let's see here. Do I need the whole page for this? No. So this sort of a drawing, what does this imply? This curved line here suggests that there's delocalization in this ligand, kind of like in a benzene ring. You know, you draw a circle. This is like a circle, semicircle. It's for 3 p orbitals that all are parallel to each other and pointing at the metal. And the electrons in this fragment and in the transition metal overlap in a delocalized fashion. So you could also write, or you know, if you wanted to make an orbital drawing of the allyl fragment, do something that looks like that. And then you got a metal. And it's making connections to all 3 of those guys. And in fact, sometimes people will write things like this. Where you have an allyl fragment and 3 normal covalent bonds. Okay. 3 normal covalent bonds is actually, it's interesting, right? Because that means 1, 2, 3 electrons being contributed to the metal by this allyl fragment. And that's the same number of electrons that you would count down here. 2 electrons from this dative interaction and 1 electron from that normal covalent interaction. These are all sort of like resonance depictions of each other. Now, you might imagine the bond to this thing is not the same as the bond to that thing. They're totally different, right? Central carbon versus the terminal carbon. The orientation of the fragment is different. So the way in which the metal overlaps with them is different. So they're not exactly the same bond strengths or something. But these 2 carbons in this molecule are identical to each other. And that's why it's fair to draw this curved line like that and depict those resonance structures down there. So count the number of electrons that the fragment donates. You can count how many L and X and Z type ligands you have around the metal. And in this case, you would count the allyl as an LX or X3 if you wanted to have those 3 covalent bonds. And that makes that thing a 3 electron donor. All right. So let's do cyclopentadienyl. Cyclopentadienyl, there's a bunch of different ways it can bind. One way is eta 1. So I forgot to mention eta, as we said, refers to the number of connections it makes. And people talk about something called hapticity. Hapticity is the same thing, okay? So this, the hapticity of this type of a fragment is 1. It makes 1 connection. What's a C5H5 ligand? Well, it looks like this. There's actually another way to draw something that has this formula here. You got a vinyl metal carbon bond. This is not a vinyl. These two are very distinct from each other, right? Because this carbon has 4 bonds to it and is planar. So this metal is in the plane of the ring here. Whereas in this case, it's sort of like sitting on top like a hat, right? So these two things are isomers of each other, which is why I drew 2 arrows instead of a double-headed arrow. And they both make a single X-type interaction. There is also A3 C5H5, which looks like this. It's basically an allo. And it's held together by this double bond, but it's basically an allo fragment. So this is sort of unusual, or we'll just say rare. It's an L and an X. And then there's A5 C5H5. That looks like that. This is very common. And so how would you describe the bonding in this guy?
L2X.
There you go. How is it L2X? Go ahead.
There's like some deal, like you've got your double bonds and those are L2 ligands, and then you've got a concentrated negative charge somewhere else on the metal, and that can act as a X-type ligand.
Well, yeah, so let's look at this version of the drawing right now, right? You've got an X-type bond here. There are 2 double bonds that can point at the metal in the same way that I've drawn for the allo fragment just above it. I've pointed one of those 2 double bonds at the metal in this drawing, and I've pointed both of the 2 double bonds at the metal in this drawing. So if it's 2 L-type interactions and an X-type interaction, it's 5 electrons. And what do you know? You have 5 equivalent carbons, all with their p orbitals pointing down at the metal. Makes sense. Okay. So when you have delocalized fragments like these, where you have, p orbitals all forming a ring, or not necessarily in a ring, but in conjugation with each other, each one will contribute 1 electron in this picture, where you're talking about L, X, and Z. All right, so we can use all of that knowledge to do electron counting for transition metal complexes and ask whether or not they obey the 18 electron rule. All right, so let's do this one. Iron tetracarbonyl dihydride. So what we're doing here, we're going to use the LX and Z to count and see whether or not the molecule is closed shell or open shell. How do you know it's closed shell? What makes it closed shell? What does closed shell mean? It means filled valence orbitals, right? And what are the valence orbitals for a transition metal? The D's, the S, and the P's above it. That's where the 18 electron rule comes from. So if you end up with 18 electrons, that thing is satisfied. You're not going to add any more. You do make hypovalent compounds, however. Okay, so the 18 electron rule is asking you whether your molecule is hypovalent or not, or whether it's a ridiculous structure because it exceeds the number of valence electrons that you could possibly put in the metal-based orbital. So in other words, greater than 18. All right, so if you want to take this one, for example, I want you to count by breaking off the ligands that you see here into neutral fragments. This is something you're going to forget. You're going to struggle with it. Break the ligands off as neutral fragments. We're going to do it again in a little while where we break them off as charged fragments. But most of the time, I want you to break them off as neutral fragments. Okay? So if you break that into neutral fragments, what do you get? You get 2 hydrogen atoms, you get 1 iron, and you get 4 COs. And those 4 COs, what do they contribute? 2 electrons each. Okay, when you make a normal covalent bond, they contribute 2 electrons. So let's count them up. This is 2, this is 8, this is 4 times 2 is 8. This thing is 18 electrons. Okay, and so that says this dihydride is closed shell. Osmosine. My 6-year-old son recently discovered Ozzy Osbourne. He really likes Iron Man. Osmosine, not named after Ozzy Osbourne, unfortunately. Let's break this into neutral fragments. How many does osmium have? Iron, ruthenium, osmium. 8. Iron is 8, and so is osmium. How do you count 2 CPs? What's a CP? CP refers to cyclopentadienyl. How do you count that? 5, right? L2X if you want, or delocalized pi system, 1 electron per p orbital. You have 2 of those, that's 18 electrons. Okay. So this thing here, A5C5H5 is L2X. And that is 5 electrons. So what people often do is they say, well, you know, Owen, I don't like this stuff because I know that osmium, that cyclopentadienyl is a nice stable thing around a metal because it's actually cyclopentadienide. And I'm used to thinking about cyclopentadienide as an aromatic system with 4n plus 2 electrons. So you can also count it that way. Okay, so if we break this thing into charged fragments, what do you get? You get 2 cyclopentadienides and an osmium 2 plus. We've been telling you all along, it's like ligand minus and metal plus. You know, the ligands kind of own the electrons, right? So naturally, you got cyclopentadienide, aromatic anion. That's why this thing is stable in the first place. The problem is that this doesn't always work very smoothly, okay? As an example, you have to remember how many of these charged things you're making. Sometimes it's very difficult to assign their charge, or there are multiple different resonance structures that you could provide. And the charge state changes depending upon the resonance structure you choose. And now you're stuck remembering, well, how did I assign this thing? And then how many of them? And oh, I have to get this oxidation state. And then How many electrons were there to begin with? -2 for, because it's 2 plus, there are all these like steps you go through and people screw it up. Okay, it's easier to count neutral fragments. Just go with me on this. It's very good to do both methods. And I do both methods, you know, my mind's eye. In this class and in general, it's helpful if you can just count neutral fragments. Okay, so osmium 2 plus, 6 electrons, 2 Cp minus, 6 electrons each. So both give you 18 electrons. But it turns out, maybe I should just put this up there to make it clear. Right? Cp minus is 4n plus 2. And it's really easy to put in a bottle. And those two methods, you know, the charged ligand fragment and the neutral ligand fragment approach should give you the same answer. Okay, you shouldn't get different answers, but it's easier to count neutral ones. And we'll do a few examples of how that's the case. All right, let's do this one. What is that thing? That's a cyclobutadienyl. How many electrons does cyclobutadienyl contribute? 5. Chances are it's 4, okay? Because you got 4 things in a ring. I've drawn this circle. It implies like aromaticity kind of delocalization. 1 electron per carbon, okay? Now, this thing also can be drawn this way. And this is not an aromatic fragment, right? It's not 4n plus 2 electrons here. There's 4n electrons. And in fact, the real structure of cyclobutadiene has 2 different carbon-carbon bond lengths. It's a rectangle, not a square. Okay, but when it's bonded to a metal, it becomes a square. It's kind of cool. Each one of these 2 can be an L-type ligand. Or you could say 4 X-type ligands, right? This sort of representation sort of looks like 4 X-type ligands. It's a 4-electron donor. So let's break this thing into neutral fragments. Iron 8 of 4, C4H4, and 3 COs. Iron, ruthenium, osmium have 8. 8 of 4, C4H4, we've decided is a 4-electron donor, either L2 or X4, or you could say LX2 if you want it. 3 COs, 2 electrons each for carbon monoxide. Carbon monoxide has a lone pair, okay? CO is a 2-electron donor. That's 6, and that gets you 18 electrons. Good one here. That's what's called CP star, cyclopentadienyl with 5 methyl groups, 1 on each of the carbons. And then this thing here, this is called trimethylene methane, that fragment. This is an A4 C4H6 fragment. Trimethylene methane. All right, kind of funky. Let's break this thing into neutral fragments. CP star, this is the same thing as C5Me5. Okay. How many electrons for CP star?
It's still an 8 of 5, right?
Yeah, 8 of 5, C5Me5. That little circle with the line in the middle of it means 8 of 5 in this case. How many electrons?
5.
Same as cyclopentadienyl. 1 per carbon in the ring. L2X or X5, however you want to say it. How about tantalum? Tantalum is 5. Vanadium, niobium, and tantalum. How about a methyl group? How many bonds does carbon make? 4. 1 of those valence electrons is being used to make a bond to tantalum, so it's an X-type ligand. Two CH3 fragments. What do you do with this mess? Go ahead, Matt.
You just look at each single bond that's going to and each type bond that's making electrons that are bonding with.
Yeah. So you could say, all right, every one of these is a normal covalent bond. This carbon is making 4 bonds. 1, 2, 3, 4. Same one for these. What about this guy? 1, 2, 3, 4. That's one way to think about it. Let's redraw that for a second. So I'm going to draw a double bond here. Now, what do we do with these CH2s down here? How many bonds does carbon make? I have 3 bonds around it now. So you got to have a free radical here and here. Okay, and there are 3 of these. So you could say that it is an LX2 ligand if you wanted. This thing it's a pi system, right? It's not a ring, but it's delocalized. So this thing probably has D3H symmetry. All carbons, all of the CH2s are identical. Okay, so if you pull the fragment off as a neutral thing, then you and draw the resonance structures of it, it becomes easier to count. Okay, so 4 electrons for that guy. A to 4, C4, H6. That's 16 electrons. All right. Now, 16 electrons is not 18. Right? Get the math right there. So what does that mean? 16 electrons. What does that tell you? There you go. Wants to get to 18 means that that compound is hypovalent in the 18 electron picture. And what do hypovalent compounds have? Empty orbitals. That tantalum center, despite the fact that it is surrounded, has an empty orbital, and you could stick a ligand to it if it's small enough. Tantalum's pretty big. There's room, okay? So 16 electrons means hypovalent, and there's an empty orbital on the tantalum center. What does that look like? It's not a very good drawing. But it's 2 allyls around a nickel. Okay, nickel diallyl. Nickel has how many electrons? Nickel, palladium, platinum have 10. These are A to 3 allyls. There are 2 of them. How many electrons? 6 total, 3 each, right? It's an LX ligand. There you go, 16 electrons. That nickel has an empty orbital. Let's do another one. Tungsten hexamethyl. How many electrons for tungsten? Chromium, molybdenum, tungsten have 6. Chromium's just to the left of manganese, just to the right of vanadium. Chromium has 6. Chromium, molybdenum, tungsten all have 6. 6 methyl groups. How many electrons per methyl? 1. 12 electrons. A lot of room around that tungsten. That's an octahedral compound. And a fireball, that's a flammable substance right there. So tungsten can take 6 more electrons to fill its valence shell. So this compound is octahedral. You got an EG and a T2G. This is sigma star. And it's got no d electrons. Okay. This thing here is non-bonding in this sort of a complex. Totally empty. Where are these on the metal? Where are these orbitals? In between the ligands, right? The sigma bonds here in EG are Z squared and X squared minus Y squared. Those point at the ligands. These T2G orbitals point in between the ligands. An octahedral. All right, so in between the ligands, there's an empty d orbital waiting for some action. How about tungsten hexacarbonyl? Tungsten is 6. These are 2 each. This is 18 electrons. How many d electrons does tungsten have? Those COs are all L-type ligands. There's no normal covalent bond being formed there. So the tungsten is not using any electrons to make single bonds to those COs. Okay, so this thing has 60 electrons on tungsten. It's an 18 electron compound. This is a 12 electron compound. They're both octahedral. Both have 6 ligands, carbon ligands for that matter. They're totally different molecules. Tungsten hexacarbonyl is a rock. You could probably eat tungsten hexacarbonyl. Wouldn't recommend it, but it's stable, thermally stable. You can sublime it. It's a rock. So this thing, you've got a sigma star and a pi bonding orbital now. And you have 6 d electrons in those pi symmetry orbitals around the tungsten center. Totally different substance. No empty orbitals. 18 electrons means it is full. So when you go to a talk by somebody who's presenting transition metal chemistry, one of the things you should be doing is counting electrons. If you get bored, just start counting electrons. He was first, yeah.
This geometry, I'm just looking at that tantalum compound. Like, how would we describe the geometry of that? It has so many bonds.
I would describe it as a mess. It does not have a well-defined name, and its shape doesn't have a well-defined name.
How many bonds would you say it makes? That'd be like 4 plus 2 plus 5. 11 total.
Yeah. But they're not all the same.
So far, we've always been like, it's like 6 is the maximum. That's not big.
Definitely not. Margot?
Do you mind explaining why in tungsten hexamethyl there are no d electrons? Like, where are the d electrons from the tungsten going? And then why, if it's a full, why are there no Eg electrons on the hexacarbonyl?
Why are there no d electrons on the hexacarbonyl?
On the hexamethyl first.
Oh.
Where do they go?
So how would you describe a tungsten methyl bond?
Covalent.
It's a covalent bond, okay? And if you had to say who brought what to the party,
They each bring one.
they each bring one, okay? So, and there are 6 methyl groups. So that means tungsten had to give up 6 electrons to the surrounding methyl ligands. And it started with 6, so it gave up all of its electrons to make those covalent bonds with the methyls. That's why there are none left.
So would that mean in the, like, if we were to draw the full MO, those electrons would just be in sigma bonds?
Correct.
below?
You got it.
So they still exist in the greater MO, but
Yeah.
if we look at these d electrons as like localized on the
There you go.
tungsten,
Yes,
they're just not in this picture.
you got it. They're
Okay.
part of the normal covalent bonds, which is way down low. Those are the bonding orbitals. CO is different because CO brings both of the electrons. Okay, and so the tungsten retains 6.
Mhm.
We're going to talk about how it uses them to make back bonds and what that does to the picture next. But that's why it's different. Yes.
Okay.
So if we're doing electron counting for the tungsten methyl.
Yeah.
With the charge fragments, is methyl a plus one?
In the charged formalism, the ligand is minus and the metal is plus.
So would there still be 6 electrons on tungsten in the charge? Or would there be 0?
There would be 0.
Okay.
Yeah, if you pulled out 6 methyls, they would come off as methide. And one of the problems with that is that that's not always true, meaning that sometimes ligands are more or less electronegative than the metal, depending upon the ligand type. Hydrides are often not electronegative enough, and the metal outcompetes the hydrogen for the electron pair. Everybody counts it like H minus, but it's not H minus in those compounds. So confusion ensues because everybody's assuming, well, it's ligand minus and metal plus, because that's what you're taught. That's how you count electrons. But that's not really the real charge on the metal. So it's not fair to say that the oxidation state is representative of the real charge on the metal,
So
because electronegativity is a complex issue. Yeah.
would you say that the charge of tungsten is 0? Like actually 0? Or would
The
it be
real charge on the metal is something you could measure with a spectroscopy. That's different than oxidation state. And oxidation state in most people's minds is really ligand minus metal plus, which is not a true description of the compound. For tungsten hexamethyl, you would say that there are 6 methyl minuses and 1 tungsten 6 plus. Okay, and tungsten 6 plus has no d electrons left, and that's why the diagram has no d electrons in that octahedral splitting. Okay. Tungsten hexacarbonyl, you pull off as a neutral because it's just dative L-type thing. You don't pull it off as a negative in that case. You pull both electrons off and you get a neutral fragment. In the methyl case, you pull both electrons off and you get a charged fragment. Okay, is that clear? So sometimes you're going to run into compounds that have a charge overall. This thing so you saw that. What do you do with that? What is this thing, first of all? Sort of a poorly drawn cyclohexadienyl. What's a cyclohexadienyl? It's a C6H7. Okay. Let's count some electrons. Iron has 8. What do we do with this thing? 5, okay. Same situation, delocalized carbon-based fragment. Just sort of count the number of electrons, 1 per carbon. So 8 of 5, C5H7 contributes 5 electrons. 3 COs, 6, because each CO brings its lone pair up. So that's 2 per carbon monoxide. That's 6 electrons. What do we do with this negative charge? Where is it? If you had to assign it in the molecule, where would you put it? Well, there's no formal charge in this drawing. If you were to assign formal charges, you might put plus here, sorry, here, and minus there. Remember that? We don't do that because it gets all funky. Negative charges like this belong to the metal unless there's a formal charge somewhere, okay? So if I were to do the full formal charges, this thing would be 4 minus, and there would be 1 plus on each one of those. The minus goes to the metal, and it contributes 1. Okay? We're going to do more of those. Now, 8, 11, and 1, that's 20 electrons. Alarms should be going off in your head. 20 electrons, that's bad news. There are not enough valence orbitals on the iron. Something's wrong here. That's not a stable molecule. Good thought. It may not be a tricarbonyl. It's probably a dicarbonyl. Okay, if it were to exist, it probably does exist. I'm almost 100%. Somebody's made that, and it's a dicarbonyl. Okay, so you'd be surprised how many times you see stuff like this. People write mechanisms out, and they write something with more than 18 electrons, and if you're feeling combative, you can call them on it. A very famous professor, who shall not be named, at their faculty interview when I was a student at Caltech, drew a 20 electron compound up on the board. Nobody said anything, but and there are probably a lot of people in the audience kind of going, it's too bad. All right. Let's see here. I like this. Pretty, isn't it? All right, cobalt. How many electrons for cobalt? Cobalt, rhodium, iridium are in between iron, ruthenium, osmium, and nickel, palladium, platinum. So there are 9 electrons for cobalt. Let's do a minus charge here. We'll give a, where's that minus charge? I don't see any minus charges really, so I'm going to put it on the metal. 2 cyanides. How do you count a cyanide? 2 electrons per cyanide or in total? 4 total?
It's a single electron. It's a single electron. It's 2 electrons.
Well,
It's 2 electrons.
okay. Anybody have a problem with that? Nobody? You go?
Yes. Yeah, I have, yeah, it's a 2 electron donor.
Okay. Why do you say that?
Because it's I mean, the cyanyl group is it's a pi donor, right? So when it makes a bond with the.
It's not a pi donor, no.
A pi acceptor.
It is kind of a pi acceptor. It's kind of a wimpy pi acceptor, but it's a pi acceptor.
Oh, it's a sigma donor.
It's a sigma donor. It's isoelectronic with carbon monoxide. So yeah, you might say, oh, there's a lone pair on that carbon. So how many people like 2 electrons for cyanide? How many people like 1 electron for cyanide? 50-50 split here. Break it into neutral fragments. You don't think of cyanide as a neutral fragment. You know, cyanide is an anion. Hydrogen cyanide is a gas, but it dissociates into H plus into cyanide minus. So yeah, it's like 2 electrons on cyanide, but that's if it's charged, and we're not doing that. we're doing neutral fragments. So what's the neutral fragment? Cn dot. That's a 1 electron donor. That's an X-type ligand, just like a halide. Okay. So you don't like that because you're thinking like cyclopentadienide. It's a 6 electron pi system. It's a ring. Use neutral fragments. So cyanide is not cyanide as a neutral fragment. It's cyanyl. It's a radical. All right. So 2 of these guys gives you 2 electrons total, and 1 carbon monoxide also gives 2 electrons. 1 carbon monoxide. So those 2 things are isoelectronic. They have the same number of electrons, but one of them is charged and the other is neutral. When we break things into neutral fragments, that cyanide becomes a 1 electron X-type ligand, and the carbon monoxide becomes a 2 electron L-type ligand. All right? Break things into neutral fragments. You're going to get confused. Go with the neutral fragments. Remember that. You're going to cut corners. Go with the neutral fragments. Sorry? Ah, whoops. Thank you so much. Phosphines. What's a phosphine? It's a very smelly compound. Trialkyl phosphines have a great smell. What's that? L-type ligand. It's just like NH3. It's like NH3's big brother, right? I would say big sister, but unfortunately, trialkyl got a pretty rotten smell. I sort of grown to like it, but you know, it's an acquired taste. The blue cheese or something like that. Triethylphosphine is a very like peppery, metallic, skunky kind of, I don't know how you describe things that smell like it. There are 2 of them. There are 2 electrons each. (10, 14, 18). Okay, so that negative charge contributes 1. Cyanide is a 1 electron donor when it's a neutral thing. All right, so another trick for this kind of thing, which I really like and I do all the time, is I mix the charged and neutral formalisms. Okay, this is like advanced electron counting. Prepare yourselves. Let's take this cyanide complex. We're going to dissociate Cn minus. Okay, let's pull off the cyanide. You know, you're right. Cyanide, it's like an anion, right? That's a very neat fragment to dissociate mentally. You get rid of that, and what do you have left? Okay, we took off cyanide minus, so you better get rid of that negative charge. Okay, that's what you have left. This thing is sort of easier to count than having to deal with this negative charge. I promise you'll see examples of that. 2, 4, 9, 2, and 1. 2, 4, 9, 2, and 1. This is 16 electrons. This cyanide minus, you could think of as a 2 electron donor. Okay, so this fragment here is 16 electrons. This fragment here is 2 electrons. It's negative now. We're not doing a neutral fragment, we're doing a charged fragment here. But it has a lone pair. And that lone pair can bond to this 16 electron compound to make this one. So when you bind this lone pair, how many electrons are you contributing? 2. Okay, so the negative charge here can kind of be dealt with by just like chopping it off and thinking about it as a 2 electron donor that's negatively charged. There are going to be times when that is a useful trick. Okay, You guys clear on what I'm trying to communicate here? Yeah. Normally, we don't break things off as charge fragments, but sometimes it's useful to do it. Especially when it's simple, like chloride, fluoride, that's a negatively charged thing. Easy to pop one of those off. Okay. I'll save the next types of compounds for next time. Does anybody want to ask a question at this stage?
I want to ask a question about the radical or the C dot.
Yeah,
The cyanide, so it is a pi acceptor, but it's a weak pi acceptor. So that means that it's more resistant to like taking the electron from pi back from the middle. Right? It's not going to be willing to do that. It's not much of a conduit, say, as the carbonyl or carbanion. Right? So the
Yes.
carbonyl can take more electrons. So is that why it's able to donate to? Like, is that
No.
not why it's not meant
No.
to do?
you could say they both donate too if you count cyanide as a charge thing. We're counting it as a neutral thing. And that's why we say cyanyl, you know, CN dot, because we're breaking into neutral fragments.
It's a formalism for counting.
It's a formalism for counting electrons. It's not a statement about what the molecule wants to be. Okay, stick with the formalism and life gets easier for you. We sort of broke the formalism over here to make our counting a little simpler if we get confused. Neutral fragments are the way I want you to do it if you can, okay? Break into neutral fragments for counting electrons. All right. Yes. Oh, that's a typo, yeah. That should say C6H7. Contributes 5 because there's that semicircle there is over 5 of the 6 carbons. Okay, so each carbon then has a p orbital that make up a pi system that can bond to the metal. You could also think about that fragment like this. All right. This is a cyclohexadienyl radical, 2 double bonds and 1 electron. And there are other resonance structures you can write where you have a double bond here and a radical there. That's the 2LX, exactly. There's the LLX, that's 5. And just like any other, you know, delocalized aromatic system of p orbitals, generally when you see that, it's 1 per carbon. Yes.
This has 3.
Yeah, the oxidation state is a measure of the relative electronegativities of the atoms around boron. Fluorine, nitrogen are both more electronegative than boron, so all of boron's electrons are gone. No, because boron starts with 3.
So there are 3 flowing in 1.
Yes,
So you're not counting the nitrogen.
because the nitrogen owned the electrons that were used to form the bond in the first place. So in the case of the boron-fluorine bonds, they are normal covalent bonds. 1 electron is contributed by the boron. But in the borane-ammonia complex, both electrons are contributed by the ammonia. So the oxidation state counting is about the number of valence electrons being given up to the surrounding ligands. And, you know, yes, ammonia is more electronegative, but boron only had 3 electrons to begin with. You can't go to an oxidation state higher than the valence number.
Okay, got it.
Yeah? Okay. All right. Yeah, you're welcome.